Here comes sort of like the more interesting part, the comparison between performance of like how, as first size and then performance. Here's the size. This is a raw text file of 750 gigabyte, right? 750 gigabyte. That's the original file. That file compressed with LZO is like about half the size. Snappy with the sequence file is about half the somewhere there, half the size. Averroll Snappy, sort of like as soon as you just compress it and sort of give structure, you somewhere hover around the half size mark. Then over here we get towards Parquet with Snappy compression, and you can see how this further condenses out of the already compressed by orienting, just rearranging the data. You get a much better compression ratio. Right? So this is much smaller than what you expect. Right? So this is pretty good. And this is Snappy compressed, which is Snappy is a very lightweight compressor. It's very fast. It hardly needs any CPU. While if you use one like gzip, for example, which is very heavy on CPU, you can get nearly the same compression, but it's very costly because like uncompressing and compressing in gzip is very much CPU intensive. So the best sort of alternative is using Snappy, which is fast, and then Parquet gives you the same size savings. And performance-wise, look for the purple bar. The purple bar, the lower the better. You can see how text and the other ones, the red one is sequence files with Snappy and so on and so forth. Parquet with Snappy compression. I don't know what this Q59 is from the TPCDS query suite, as a test suite. But over here is still basically faster than the others, but it gets a bit higher. But overall, the purple, here's another one of those hot ones, is faster than all the other. What does it mean to Twitter? For Twitter, this means just by converting from the original Thrift data files to Parquet with Snappy, they saved that much space, 30% space savings. And imagine you have multiple thousands of computers sitting around storing data, and you can save 30% of storage. That's huge, right? Maybe on a 10-node cluster, it might not be that obvious or so, but as soon as you go to larger clusters or so, that's a huge saving, just by having a better file format. And now we look at the performance at scan time, because we want to be as fast as possible. We're still on that side of the high throughput query engine, so how can we be fast? We said we just look at what we need. We do this column oriented. And you can see this here. If you do like a single column out of, this is an example out of 30, you basically add 10% of the original time. So 10% only of the original time to run that query. Only if you hit all fields, so somewhere here at 29, you're as fast as the original query. And if you really if you do a select star on Parquet, you are basically 10% slower than the original file format. So it is a slight cost if you do a select star. But otherwise, as soon as you go anywhere into like a more selective query, always gain. So this is a really good file format for sort of analytical queries, because it really gives you that trade-off. Those petabytes of storage saved. And if you look at these jobs, they have a big job here, for example. They read 30% less data of disk, which equals to 20% of task time saved. They have a scalding job, which is this cascading Scala, where they read 14 out of 35 columns, which means they're reading 80% less data and 66% time saved on job runtime. It's tremendous, just doing this. Again, as I said, this is just evolutionary. It's very nice and very good to get to this point. Now let's switch to the other side before we bring this all back together. Let me real quick tell you a bit more about how HBase looks like. Right? We have done the query side. Now we know how now to optimize. All of you are now ninjas to do queries really fast. At least you know how this is being done. So if anyone comes to you and says we can do it really fast, ask them how they do it, and you should find yourself in that space somewhere. You should see the concepts. There can't be anything else. Compression, layout of data. It's the only way to do this. So here you can have an FPGA that compresses even faster than Snappy, whatever, all these sort of like hardware accelerators, but they don't buy you much more in these days. So you will see them slowly going away, I would think. We'll see. So how does HBase do this? HBase is different to the high throughput, large scans ideal for analytical queries, workloads that you see on the query side, on the SQL side, with Impala and other systems there. Here we have something where you can do scalable, multi-dimensional, random access, right? And how does it look like? We have a table that's very similar to a database table. Here I'm using more or less like like every row looks more like a spreadsheet in Excel, right? But instead of having a spreadsheet on Excel, or instead of having a table in a database, if you look at this closely, you will see there's something off here. What's off here is that every column has a different name, right? Every row has different column names. The first one has column A, column B, and so on and so forth. The last one, or the second last one, has a date in there, like 2013 or whatever it is. That's odd. The thing is that, similar to what you heard with Parquet taking out those missing fields, similar here we have a way in HBase to only store what is being set. Which also means you can't have an empty row in HBase. It doesn't exist. You need to have a value that you put into a row, and then that value, and only that value in that row exists. There are no nulls. This is completely, for someone who does databases, it's weird because you have to patch in nulls everywhere. And here you don't. And you have two built-in indexes, sorting only one direction, which is also weird, right? So because typically you have like multiple indexes by every field, and you can sort up and down. Here you only have two indexes. The first one, the primary index, sorts the rows by row key. It's different. A row key, think of it as a primary key in a database. Typically, a primary key in a database is a specific column that you declare to be the primary key of that table. Here, we only have one column, and that's called the row key. Right? And that column is also used to sort all of the rows. So if you insert a row A, then D, and later on you insert row B, it gets sorted automatically in between. So it's like in Excel, you insert it, you go to row, say you have A and D, you click on D and say insert new row above. And then you insert your row in there and type it in. So you can, in the Excel, you can do the same thing, but manually. Here it happens automatically. And the second sort you have is per row. You have an index going that way, horizontally, which is within each row, each column name is sorted as well. Here, ascending is all ascending. Weird thing is though, if you look at this sorting, this doesn't look like human sorting. This is actually binary sorting. It's called lexicographical sorting, which means it just compares byte by byte in the key. And because this is 1, 1, 1, they're sorted first. And then 2 is greater than 1 on this position of the index. And therefore 2 comes in at the very bottom of this example. If you really want to have that human readable, you have to prefix that number with the zeros or so and make this human readable, like prefix it. But that's just basically just the way it works. Same with this sorting this way. Now, how can I use this? The good thing is, for example, if you had, say, you want to store an RSS feed, or like a time series database, or a stock ticker in HBase, you can have a row per ticker symbol, and then insert a tick with the name of the column being the time when the ticker happened. And now when you do this, you always have the oldest tick at the beginning and the newest tick at the end of that row, because it gets sorted automatically by column name. Now if you insert, say, you can see this here, on the 23rd, you get this column, in the 24th, this column, in the 25th, this column. And again, if I miss something and insert this later, it automatically appears at the right position, so you don't have to like update something, you just insert, and it sorts it for you in time series. But typically what you want to have in an RSS feed is the newest 10 posts. Because if I present someone the oldest 10 posts, they would say, great. But I read them like 2 years ago because it's when I started subscribing to the service. So it's better to have the newest one first. In this case, you have to do this yourself, do a bit inversion of that date, or in this case, take the longest value that you have, the max value of that field. In Java, it would be, for example, integer.max value, and subtract the epoch from it. And this turns it around because now you have an ever decreasing number instead of ever increasing number, and now you have the newest value always at the left-hand side. So all you have to do is say, from this stock ticker, give me the first 10 symbols, or 10 columns. From this stock ticker, the first 10. You merge them together, and you have the newest 10 entries for those two stock tickers, or for all of them that you have stored. So you can very easily build time series information on top of HBase. The other thing, yeah.
What kind of data structures are used for implementing?
Yeah, good question. What is stored inside these fields, right? It's all binary. Everything's binary in HBase. We have no typing. So you can basically store whatever you want. There's a library that helps you translating, say, from Java long into a byte, or from anything else. But there are libraries that run on top of HBase that takes an arrow record and encodes this into a field, into a column. So it's up to you to really interpret this.
My question was more, is it the B tree or what
Oh,
are you
yes.
using?
No, I think I have, yeah, you will see in a second. I have a screen for that, slide for that. Because that's important, because then we can really understand why things are not as fast or whatever on the scan side. I get to this one. That's exactly where I'm working towards. How is it actually stored? Right, so let's, we're still on the logical side. We're still on the sort of the, how does it work on a higher level? The one thing that I didn't talk about is multidimensionality. Oh, again, mind blown, right? What does it mean? It really means, instead of having a database, when you override a column, it's gone, the old value is gone. Unless you have a backup, it's gone. You're overriding it, and a new value appears in its place. Here, because of its storage, where we get to, we actually maintain as many back versions as you want. Default was 3, now it's 1. This was recently changed. And this is the multidimensional part, which means if you store something in HBase, and you're overriding that field at this row column coordinate, it actually keeps a timestamp with this entry. If you write a newer one, it keeps all of them backwards. There's a background process that throws out old ones, so if you have configured 1, there will be actually for a short amount of time 2, and when that background process says, oh, there's an old one, you only want to have 1, this one you have 2 actually somewhere, throw that one out and it will disappear on you. But if you query it, you will only see the newest one. If you switch it to 3, you have the choice of 10 or whatever, 1,000 versions. You have the API gives you the power of saying, give me everything between that time and that time. Remember time series data? You can actually query the database. I mean, once you store this in HBase, you can say, give me the data or that entity, how it looked like 2 hours ago, or 2 days ago, or 10 days ago, by setting the timestamps of the cells you want to have returned to a specific time range. And because everything is still stored backwards, you can actually say, all right, I want to see how the world looked like 2 days ago. You can do this by grabbing only the cells from 2 days ago, ignoring all the newer changes. And that is possible too with HBase. Again, this has nothing to do, if you think about what we heard earlier with SQL and querying data, how do you model this in SQL? There's ways, of course, yeah, I mean, people get creative with SQL, right? Which means the person next to you might not even understand what you're currently doing, right? So if you move away or if you hand this over to someone else, the chances are quite high that the next guy doesn't even know what you did there, right? So here it's naturally, it's built in, we know there's timestamp of everything. So everything you can actually think of it as a text spreadsheet with a little drop-down box, and you can actually click on it and see previous versions. If you don't specify anything, you get the newest entry. If you want to, you can ask for older entries or for specific older entries. Here we're getting now towards the storage side. There's one more concept on top of HBase that you have to understand. One is the partitioning. We need to grow, we need to scale. To scale the unit of scalability in HBase, it's called a region. This happens automatically for you, or you can pre-calculate and help the systems bootstrap your table. But typically it happens automatically, which means as you start a new table, you have a single region hosted on a single region server somewhere. And as you insert data into that one, it gets split into 2 regions once it hits a certain size. These days, 10 gigabytes or so. So 10 gigabytes is the default size of a region. So if you had 10 gigabytes in this one region, you split it into 2 regions, 5 gigabytes, and you start filling them again. You don't have to worry about where they reside. You just have a client saying, insert something into row 100 or into row 1000 or whatever it is. Where it goes to, the system does for you. It routes the request to the right server and it stores it. And the other thing that we need is to perform queries most efficient is to do this sort of column-oriented layout where we in HBase have something called a column family. Data that you need to query together, you put into one column family, which is stored together in a specific directory. And data that you query in other queries that you do not need with this set of data, you put into another column family. And these column families help you to separate data, not on the column level, but on a larger scale, a little bit larger than what we saw earlier, where you can do per column, and you can bring it down. We saw this with the speed up at Twitter to really, really fast performance on a single column. Here we have not that concept. We have, unfortunately, only sets of columns. So it's not as optimal.
You mentioned before the idea with the ticker symbol and with the stock ticker. So could it be that in this symbolic that region 1, region 2 could be, for example, region 1 Eurostoxx 100 and region 2 DAX 100 and Dow Jones, and that you build such regions and have fast access if users just like to have access to Dow Jones values, or
exactly.
Is that,
but that is something, if you had to have the system build your table organically, it might not match this concept. If you know that you want to achieve this, you can instrument the system saying, when you create the table, build the cuts at this point. So everything that starts with a certain ticker symbol should be in one region, and the next region should start with another ticker symbol, another set of ticker symbols. Yes, you can do this.
So it's something comparable like chip design, that you pre-design that in the case you would like to have the fastest access and what the patterns of your customers are.
But that's basically, when we talk about sort of complexity, that is the black belt part of NoSQL in general. Getting the schema right to have the most efficient reading is much more involved than what you saw when you just use Parquet and SQL. It doesn't give you the full power of like what we have with the time series or whatever on the schema side that HBase gives you, but it automatically sort of like creates by every column anyways that layout for you. While on the HBase side, you need to decide this for yourself. The system gives you no guidance. You just have all of the tools at hand, and what you do with it is your own thing. So if someone gives me all the parts for a house and all the tools, my house will probably be crooked. If a builder does it, it probably looks perfect, right? And this is the difference between black belt and me being a white belt or whatever in house building. And that is sort of the thing that I think is the most difficult these days to get right. But as I say, there's lots and lots of information out there. You can read into that. There's a book as well on that. Just saying. The thing is though that this sort of comes with you, as you use it more often, you get into that sort of thinking, but it's not automated. Right, so let's move on because we want to go to the summary as well. I think everyone is ready for the dessert. It's going to matter. Wait, if you want to have dessert, you can go and grab one now. Otherwise it's gone. The architecture, it's very similar to what you probably, if you know Hadoop, it's very much similar here as well. You have an API on top, we have a master, multiple masters for failover that orchestrate the cluster, making sure that all the regional servers are up and running. You have the region server responding to requests. Underneath you have, we get to the storage now, you have H files. They are storing the data, and I'll show you how this looks like in a second. You have a memstore component, you have a write-ahead log, and underneath you have the HDFS storage and Zookeeper for keeping state. Zookeeper is I call this a neural network. So it's basically our way of saving what's happening, so that if you shut down HBase or you move a master to some other place, that's the one point of truth where we can say who's currently active, who isn't. It's just sort of like bootstrapping and keeping the cluster healthy. It's very small component. It's just like an oracle or some sort of important part. Yeah, so this is basically the clients mostly communicate with the stores. You see this here, again, you have to memorize this for the test later on. It's very small, I know. Don't strain your eyes. The important part is HBase on top, HDFS on the bottom. We store data in these store files, HStore files or H files underneath. These are chipped into blocks. They are by default 64K size. Remember Parquet when I said we have these pages? You can tune the page size, so you can tune the block size in HBase. But the default size is 64K. This again, when we talk about optimizing HBase, is an important factor. Depending on your access, how much data you read from a row, you might want to reduce this block size so you don't waste cache or whatever it is, I/O, on data that you don't need. If you read a lot of data next to each other, then you might want to increase the block size so you get larger blocks in one I/O and you can scan data faster. We'll get to this again when I show you the comparison. But that is arbitrary to HDFS. HDFS has no clue what HBase is doing. It's just a binary file for HBase, for HDFS. HDFS just opens the file, stores the file, and closes it. So there's no connection, but HDFS keeps our data safe. It does the replication of that data across multiple nodes. So if you were to run HBase without HDFS underneath, you might be in trouble. Right, because we need to have some sort of file system that keeps it safe, right? So in this case, it's just sort of the way it's been done. The way it's been stored is called log structured merge trees. That's an interesting paper that came out years ago. And again, Bigtable picked this up as an interesting paper. The way that, when you looked at B-tree-oriented databases, B plus tree or B-tree-oriented databases, they have this problem that they have these little pages everywhere, or basically written as a tree, and as you update that tree becomes imbalanced. And if you remember, some databases you have to eventually run an optimize command so that rebalance everything, so that things go like, look at Windows defrag, right? This is the same thing. You fragment it, and you have to run a defrag to get everything back to next to each other. And to get away from this one and to be faster on disk, all of the previous databases were hindered by IOPS. Whenever says everyone will hear IOPS, you're like, well, how much IOPS can this do? How much IOPS can the system do? How much IOPS does it need, or whatever it is? IOPS is the only reason to talk about IOPS is that in a physical spinning disk, it needs time for the head to spin around, find a place on the platter which turns around, and as you basically have positioned your head, you wait for the data to come flying by. Right? You have to wait for the disk to spin. All of this sort of like seek time is really costly because you have to have a physical arm that moves around. Right? This is why SSDs and these sort of other things today are really interesting. But on platter, you wait for physical things to move. To get out of this problem of moving ahead for every small thing that you update in the B-tree in the different places on your platter, they shifted away from having small units into sequential writes. When you write sequentially and read sequentially, you can saturate a disk. Only then you can saturate a disk. Otherwise, you're hindered by the physics of the head moving around. And log structured merge trees does that. It writes sequentially into a write-ahead log. It appends at the end into a write-ahead log. And when it rewrites files on disk, it basically does this in a merge sort by taking two sorted files, writing them sequentially into a larger, newer file sequentially. So reads sequentially two files and writes into a double size sequential file again out to disk. And everything in HDFS, to complicate things, is immutable. So once I've written a file, I can't update this file anymore. So how do I update it in general with HBase? How can I update a small data point? And the way this is being solved is by writing tombstones. So when you delete, you actually write an update to this column and say this column is now deleted. And the background operation takes care of taking this tombstone marker, and when it rewrites the files in the background to do housekeeping, it finds the tombstone and says, oh, everything after this one is being deleted. So when it finds a entry that is basically masked by this tombstone, it just drops it on the floor and it merges into a new file. Right? So this is like, it has to happen, but we have some background operation that need to run, otherwise you might have an ever-growing data working set. So it keeps on growing because you're not throwing anything out. You have to run these background processes and they will take care of this one. But it adds to your I/O. Again, we talk about scan time in a minute. This will cost you some time in the background. Right? Let's go. So I want to get to the summary real quick. This is how it looks like physically. You have the table. The table is split into regions. The regions are then hosted by exactly one region server, so we get strict consistency. That's different from, say, Cassandra, which has eventual consistency because you have multiple replicas of the data. And the newest trend in HBase is we also get region replicas, so in the future you can do a sort of like a half-assed eventual consistency on top of HBase as well. Yeah, we can discuss this over a beer later on, but the idea is that HBase is typically strictly consistent by having one server respond to a set of roles. And only that one server is the one who writes into the write-ahead log and updates data on your behalf. And the client client talks directly to region servers doing the work. Going back to the storage, how is it actually being stored? The data is being written from disk into, basically from the logical view. That's again the table from 1 to n. Here are the column families, and I told you the column families separate sets of columns into groups. And so we have two groups here, column A to C and D to G. And here, over here we have two regions. They're also, this is row 1 to 99 with 2 column families, and this is 99 to 199 with 2 column families, and all of that lands in a separate directory on disk. You can actually see them. If you go to HFS, you can do an ls /HBase /table name or as data in between info or whatever, and then you basically see exactly that structure on disk, and you can work with that, which is quite nice. So underneath you have then files, and you use these column families for specific features. So you can actually tune those for example, different compression types, different time to lives. If you want to have this column family being cleaned up quicker than the other one, or not at all. So this is where you typically spread them apart. But you're not having the fine granularity of a column-oriented file structure. Let's look at the file format. And just, as I said, I've already mentioned this. It's open source again, it doesn't really matter much. 64K by default, I mentioned this, is the block size within each file. And you will see how this looks like. And don't worry about this data, I'll just show you the image. It's the same thing, just as an image. This is how it looks like. We have a file on disk, which has data blocks, 64K by default. Then some optional meta block, and then a trailer. And the trailer here indexes gives us an index, and that index into the data gives us index into these ones. But on a 64K border. So every 64K we have an index. Because that index here points to this beginning of the block, that beginning of the block, and so on and so forth. So we cannot tell if you have a specific column typically. We can only say there are columns from A to F in this block. So you might have a B, or a C, or a D, I don't know. I only know you have an A, we have an F that continues over here. So in this block, if you have that, if you want to have column B, there should be in this block, but I can't tell you if it is. So what we do then, we load this block 64K, we look into that block and say, no it's not, or yes it is. And to speed this up, we have like Bloom filters, so we can then say, oh, does this block really have B? And then the Bloom filter will tell us, oh no, this block doesn't have B, so we don't have to do this. So again, we optimize the performance, but we only can do at the 64Ks border boundary. We have to load these 64Ks to do some work. Right? And this is again 64K spread across H file. The H file is being spread across the HDFS file, which is just a big chunk of data. So it's basically typically 128 megabyte block by default in HDFS and so on and so forth. The other block is not full, so here's the trailer, but this is basically the block spread across 2 HDFS blocks. Has no idea. Here's the Bloom filter. The Bloom filter, as I said, is really helping you to decide what has to be done. And with the Bloom filter, you see it's at the bottom here. With an index, you can tell yes, they might have this. With only the block index, we would say yes, you have to look at each of these and make sure it's there or not. If you have the Bloom filter will tell you, hopefully no, maybe, no. By the way, the Bloom filter can't say yes, they can only say maybe or no. No is great, because mostly it says no. If it says maybe, it's wrong by 1%. It's the default configuration. But 1% in all cases would say maybe, and it's not true. But it's only 1% of the time that you have to load a 64K block. And once you load this block, you see, oh, sorry, that was wrong. Only 1% of all times. So 99% of all times, you read the block or not read the block, and you write. So which means you're saving 99% of access to disk. It's a great trade-off. They need some space, and as I skip these things, I will make sure we upload the slide decks afterwards, so you can read this after you have digested the pizza and the dessert, as dessert, by the way. I will have it. There is a bit of computation of like if you want to compute how really, do I want to use Bloom filters, I say yes. They're actually now being switched on by default in the latest version of HBase. Earlier versions did not have that switch on, now it's switched on. Maybe because Cassandra also has it switched on, because now we have to do this as well. We just do the same thing. I don't know. It makes sense. Anyway, it makes sense. You typically on the safe side to switch them on than not switching them on. Unless your access pattern is completely off and it doesn't work that way, and then it's completely a waste of time, so better switch it on and take that hit. Again, this is a black belt thing. When you know what really happens underneath the hood, you know what to turn them on or not to turn them on, but you learn this over time, and it's a bit difficult. Now here comes the final 2 slides to explain how this is stored on disk. So this is why HBase compared to Impala or the other Parquet-based scanning is not really that fast in comparison. everything that you know that is basically a table. Here are some columns with some values. Here are some overwritten, like this one has 3 versions, this cell. This one has 3 versions. This one has 2 versions. It gets sorted by date as a sequential set of key values. And again here for the other column family, that's column family 1, that's column family 2. That is then stored in the store file on disk as the exact key value, like version 1, version 2, version 3, the next one, the next one, the next one. So this one here, R6, CF2, R6, CF2, C2 is this thing over here. So every key value that we store underneath the hood carries the entire dimensions that you need to find this data. If you store 1 byte in HBase, you have 40, 50 bytes overhead just to find that 1 byte. It's always like this. And again, you optimize this. There's now prefix compression, so now we can take out that pressure. If you have lots of repeating headers, lots of repeating row keys, we sort of like shrink them together. So we have answers for all of these questions, but we cannot really optimize more. We really have a bit of overhead to find every data. But that gives you the random access. If you want to update every single column anywhere in a large table, then you can do so in HBase because we know how to find it, we know how to update this. If you want to do this in Impala with Parquet, I don't know, it doesn't have it. There's no insert, right? There's stuff coming like this, but what it really does is like it writes a new file, but you rewrite the entire large file. So it's all over the place, right? So it's not really made for updatable stuff. Here we are updatable, but it comes at the cost of keeping track of where data is. And again, I skipped this. So let's go to I tested this. So this is the sort of the final part for the comparison, and then I summarize in 1 page and we're all done. I tried to figure out how fast HBase can scan raw data. I want to compare this with Impala, with Parquet, for example. I know how it optimizes on the Impala side, so how does it really optimize, or how does it really work on the HBase side? So what I did is I tried to use all of the tools so that you can reproduce this. So I used basically YCSV to create data. I used the row counter tool that comes with HBase to count stuff. I used the low-level file dump facility that doesn't do much more than deserializing the data. And I tried to avoid all of the RPCs that are in between and try to compare 2 data sets. A large one, which has 1 kilobyte of K payload. So when I say larger or large here, in HBase we do not want to have megabytes of data in a single cell. That's not really what it's built for. It's really built for, you can have megabytes, sure it works, but typically we say a couple of K is what you should have in every column. So I tested 1K against the worst other one, 1 byte. You need to have 1 byte, otherwise there is no entry, right? Because you saw that earlier, there's no key value with a value, right? You have to, but you can't just store dimensions. You have to have a value. So how to test this? I created 15 gigabytes of data, just to make sure that this actually fits into my. I have a Mac Pro at home with 48 gigs of RAM, so that I could actually cache this. I want to avoid all of the spinning disk or SSD discussion. So the whole thing fits into memory and it comes out of memory. So all I'm testing here is how fast HBase can basically scan a memory's data structure, deserialize the structure, and move from one to the other. That's the cost, or the inherent cost of finding small data points. When the data points are larger, you could imagine that the overhead of deserializing is cheaper because we only have a little bit of overhead, while if we have 1 byte payload and have a larger key, the overhead to do so, for every single byte I have to deserialize a structure that is more costly, right? And exactly that's the case. So when you look at the numbers there, the small one here, because it's the same size in total, I tested another one with 100 columns, and here I look at the first and the last. With 1 column at 1K, and this is basically with one column at 1 byte. You see here that 1 byte or 1,000 at 1K. So it's whatever kilobytes and kilobytes. And to scan that data set here, it takes me 21 seconds and 2 minutes and 8 seconds to do this on a small data set. Just the overhead of finding every little thing and deserializing this. Makes sense though, right? But if we say we use HBase for small data points to update time series date tickers, they're all small, right? And if you then want to say, now I'm scanning all of that because I've stored all of that, let's scan all of that to do analytics. That's bad. It's bad. Why? Because that's not optimized for that. You have lots and lots of small data structures. Don't do that. And on the other side, you can see the throughput. The small one, I get to like 110 megabytes. This is in memory. And with the large ones, I get to about 890 megabytes per second. Purely cached, fully cached, no spinning disk or whatever it is, to scan that amount of data. So I get a throughput of 84 megabytes per second here, and sorry, 8 megabytes on the other one. So this is like the raw scan. That's basically doing this with, this is doing this on the file system level, and this is doing this with the API. So the API is even worse, because now you have RPCs and lots of other small Java structures that come in between. So going through an API is even worse. So that's basically the answer. So when you want to scan something in HBase, you can, sure, it's built for scans. The canonical use case actually is scan. But I advise you to do this on small ranges, burst ranges. I do a couple of, I don't know, 100 to 1,000, whatever it is, of rows, that's fine. If you scan, I'd say, 1/10 of the size that you have on a Parquet HDFS side partition, say you have a partition size of 1 gigabyte, say 10 gigabytes. Say you have a partition size on the HDFS side in Parquet on HDFS, and you scan more than 1/10 of that, which is 1 gigabyte, on the HBase side, you're already faster on Parquet. So yes, you can't update on the Parquet side, but every time you have more than 1/10 of data that you have to scan, you're faster on Parquet. That's the result. So skip this as well. Yeah, so this is like the second last for the summary. So how do you place this thing? What is now the answer? So what's the sort of the takeaway? I'm confused you completely now. On the one side, on the left-hand side of this chart, you have basically high throughput and low freedom of access, which means you can already scan really fast, but you can't find small data points. You can't find the last 10 updates of a stock ticker. You can't do this in HDFS. There's no index. You would have to scan the entire partition where it resides and find it by brute force scanning all of the data, right? Which is fast with like a Parquet or whatever, and then a single digits or single columns or a few columns. It's as fast as it can be, but it's slower on the right-hand side for HBase, because HBase has to really deserialize all of these small data points. The overhead of doing this is really costly. Here you don't deserialize anything, you just do raw data scans. So it's much faster on that level. Just the friction here. I'm not even talking about the application on top that uses the data. Both would have probably the same thing. But just doing the raw scans on HBase is slow. That's what it is. On this one, it's fast because you can do optimized layouts. Then somewhere in the middle, you can increase that to like a larger block size so you get faster. But somewhere I would believe there is a hybrid use case where you then use HBase for aggregations and use HDFS with Impala for the analytical queries. Right? You have to figure out what your users do mostly. Ask them what the queries are. Look at the queries they run. Observe the queries. There are tools now that you can use to observe the queries, what they do. Just collect, summarize the usage. Collect logs. Look at the queries. Use a tool that they collect this for you, and then figure out what is the optimized case. Are they doing mostly random updates, or are they doing large scans? If you do large scans, you're probably better off on the Impala side, with the drawback of how do you do updates. That has to be solved, use case by use case. If you do random lookups, mostly, go to HBase, because that's what it does perfectly for you. If you do random lookups and scans, think about some hybrid system in the middle. Right? So this is how I see these days how it has changed from the past, where I said we had only had NoSQL and batch driven. Now we have a mixture. It's not even batch anymore. This is sort of high throughput scans versus low latency query.
Do you have a recommendation how to synchronize those?
No, there is no infrastructure, there is no middleware, there's nothing that really helps you there. This is the one thing that I believe is the big gap that we currently have of technology to use case. Like if I talk about business use case, and I want to solve them with Hadoop, everything you do in between is bespoke, custom-made code.
I think last time we were here, there was a talk from Datastax. Is this true?
Oh yeah, they have a solution for everything, yeah.
So there recommendation was to use Spark, for example, and which, if I remember correctly, unloads the data when you want to query it, and then runs with the unloaded data completely in Spark. Is there a similar concept available?
The only thing that Spark buys you there is the freedom of using a programming language to express algorithms. I/O-wise, it doesn't buy you much more. This one we have like off-heap and on-heap and on SSD caching. We have the same sort of caching mechanisms on this end. It doesn't buy you much more. The friction to de-serialize small data points, you incur this on both systems. So Spark is an engine. How can Spark as an engine solve the problem of I/O on the storage level? They can't. So I know where they're coming from, and Spark has also been hyped as the sort of the answer for the Kappa system, like the Kappa idea. Like first we had the lambdas, where lambda means we have a speed layer and a batch layer or whatever, and then everyone someone says, oh, how about we only do stream processing? That's what he sort of said. Maybe we call this. It was Jay Krabs. He said maybe we call this Kappa as an idea. It's the same problem, because we say Spark can do both. Spark can do large processing on files, and it can do streaming as well. It doesn't really solve the inherent problems of moving data around. And you need to do this on the file format that is best oriented for your use case. So yes, you can use Spark, you can use other systems on top of that. But this is a decision about, do I lay this out as a random, low latency access storage in HBase? Or do I lay this out, on the other hand, as a high throughput sequential, scannable, highly or column-oriented format? That's the decision. So I don't think we can solve this with an engine.
So
right.
Another question from HBase is, so if I think, for example, of connected cars. So I just have each car, which is a row in this, and each position where the car now is, and meter data from all the sensors in the car are stored. So now I want to know, are there any cars 100 meters around? Is there any help in HBase to do this?
No. Again, this is up to you to use that schema and the design to help you with that query. If you have two distinct queries that go exactly against each other, you have to store data twice, even sometimes. There is no way of doing this. Whenever I talk to someone and I ask them, what are your queries? And when I hear, I want to query by any column, I want to group by any column in my data set. This does not work on HBase. Because HBase, you would have to build an index for every single column to make the search, the lookups faster. And then while you're scanning this lookup index, you might still have to go back to the main one, fetch random data, which is completely bad for your cache, because you're now going randomly across this data set. Sure, you can sort of optimize it. It's not really made for that. Whenever we say brute force scanning by any column, I would typically point you to the engines, the SQL engines on top of HDFS with Parquet, like Impala plus Parquet. The problem here is, if you don't want to wait for updates, or you have to merge in deltas or something, then you're on your own on the other side. This would be coming for free on the HBase side. So this is where I had this drop, this bridge basically, with the parameters in between. There's a big area where you can go either way. It all depends on the use case. It often means nasty combinations of things. And cache validation or keeping them in sync, all of these questions, all of these things are all up to you. It's just the truth. I mean, as I said, the way I basically, you know that by now you heard me basically sort of like jokingly talk about this. But I've seen this too many times in practice. And as I said, all of the marketing comes in between. The problem is I often have to debunk the physical side of things. I have to debunk why this other system is not better than the other system. I would rather just go and say, these are the 5 systems or 10 systems or whatever it is, and they are good for this, they are good for that, or for this use case, we can have all 5 of them doing it equally bad, good, or whatever it is. Right? And the decision is really difficult these days. It might be then a political decision, a marketing decision, or budget decision, which one is the most expensive one, and so on and so forth. So no clear answer often which one is a pure winner in this case. So there is a gap, as I said, there is a gap between the two, analytical and interactive. Interactive is HBase, random access, and analytical is the column-oriented, Parquet-backed SQL engines. You can optimize HBase for larger scans, combine some data, have fewer columns, make them larger, make the block size smaller, we do random stuff. So you can optimize the I/O. You have lots of knobs that you can turn. But it's basically not as fast as Parquet would be, because Parquet is built for analytical, highly selective queries. If you scan all columns every single time, then Parquet doesn't buy you much. Storage should be more. Like storage is optimized, but otherwise it doesn't really help you performance-wise. But as I said, weigh up these sort of pros and cons and make sure what's going on. As I said, you see this basically in Impala on that side. You always have to have either brute force approaches, but because it's really fast, they often just pay off. And there will be indexes sooner or later as well. So there's work in progress. Hive already had some bitmap index or something. They already had some like first implementations of some indexes. None really took off. They're overhead. You have to maintain them, and you build the file. You have to build the index, and so on and so forth. So brute force often is the answer. Right, last slide, yay. And then you want to think about, what about search? Remember when I said, okay, SQL, a lot of people can do. NoSQL, maybe SQL on top, a lot of people can do as well. But this is all like on this one side. What about search? Search, everyone can do search. So maybe you want to really think about, how can I actually merge this whole thing with search? Maybe I can put like a Solar or something next to it and make this lookup or make this indexable in a different platform. It just complicates more things, but it is what we do currently. There's no, it's not like I would like to say this is the wrong way. It's the only way currently to do this. You have to have multiple systems. You have to keep them in sync. You have to somehow think about how do you optimize each. So there's a lot of inherent knowledge that you have to build up to get to this. Well, you know, this is not a lead up, but I could say you could also hire someone like Claudia's professional services, so I'm part of that as well. So we actually go into customers and help with that. So we're sharing our knowledge, bring people up to speed and walk away and help you with whatever you need again. But just saying it is a bit one of those, so you have to make sure you hopefully have the right intuition. Right, and there's other ways to do this, like at Spark, we already talked about this. You can have HFS caching that you can enable. So it just, as I said, there's multiple ways and nothing really is written in stone. They say there's SQL now, it's like Spark SQL, but it's not fully implemented, or it doesn't support this and that. Think about what I said earlier, concurrency, try this with like hundreds of users, not just one. One user is easy, hundreds of users is difficult. So again, whenever you hear something popping up, very carefully evaluate what you're hearing there. Right. Any remaining questions?
Do you see these hybrid solutions a lot? I mean, there's a lot of added complexity running two systems.
Yeah.
I wonder if
Yes,
most people
more
are
and
able to
more.
run one or the other. But do you see that?
Yeah, more and more.
Size?
Yeah, more and more. A single system is not good enough anymore. I see this. As I said, in the past, when the engines weren't there or they weren't fast enough, there was only like batch, and then there was like low latency random access with HBase. Now that we have this sort of middle ground with the batch is basically now demoted, it's going to go away. We're porting MapReduce over to Spark, so things go running faster. You will see that MapReduce is going to go away anyways. Batch won't be there anymore for a long time, right? So we now have these sort of high throughput scanning for analytical queries. That's why I don't call this batch and real time anymore. It's really bad. It's analytical queries and interactive queries. Sort of. And now we have to combine these two, because out of necessity, only out of necessity. And I wish that would be
It still looks like a poor workaround because the real technology is not there yet. Or?
Yeah. So that, again, I'm quite burnt, and that's why I make this sound depressing maybe, or like negative.
It does.
Yeah, it does, I know. And that's how I feel often. I feel oftentimes I go in there and I feel like, why? Why do I have to do this? Right? I just tell you that's what it is right now. There is no other way to do that. And so whenever you're marketing that promises you that it fixes that, it's a lie. It's blatantly a lie. I happily debunk all of that, right? Because I've seen this so many times. Because inherently, these are the physics underneath. Either you have to lay out one way or the other, and then you have to take either or. And there is no system currently that does, talks about database, what's it called, cracking, database cracking, where they would rewrite the files based on the access pattern. So the database would reorient the data underneath, and rewrite the files into the new schema so that it would speed up for other kinds of queries. None of that has taken off. None of that is like anywhere, it's not even like prototypes or whatever. So they typically do one thing good and really good, or not at all, right? And if you would want to do a middle ground thing where you can do both, that's where the fish are. Bad fish. Sorry. Maybe in years, say in 5 years' time, we have this conversation again. I basically go back and then reminisce about today when I said, this is all broken, doesn't work. It's not like that, so don't be discouraged. It is the right way to do this because there's no other option, right? So this is saying it is difficult, but this is the current state of the art, and if you start with this one now, it only gets better from here. So if you basically start now, and you feel like I did in 2007 and coming to today, it still hasn't changed that much, but it's gotten much more interesting. All right, dessert. Thank you.